Hi there, welcome back to the Whistlepig Classroom. We're going to continue our discussion of airplane pitch stability. This is part 2. Part 1, we talked about what stability is. Stability is the tendency to return to an equilibrium, like a pendulum swings back after you push it to one side. Instability is the tendency to run away from equilibrium, like an upside down pendulum trying to fall over. We took a look at what it means for an airplane to be in equilibrium. And we looked at the fact that an airplane has generally two wings, a front one and a back one. And the lift on the front one tends to want to make the nose go up, for example, and the back one tends to want to make the nose go down. And if those two things are equal and opposite, then the airplane's in equilibrium. So, let's talk about where this lift comes from and how the equilibrium is maintained. So we mentioned before that lift needs airspeed and angle of attack. So there is an equation for lift that contains all of these ideas in it. And that equation is really, it looks complicated, but it's not very. The lift is equal to 1/2 times the density of the air times the square of the airspeed times something called CL alpha times the size of the wing. So here's the airspeed part. If you double the speed, you get 4 times the lift. And here's the angle of attack part. The angle of attack times all this other stuff gives you more lift. So if you double the angle of attack, you get twice as much lift if all these other things are the same. For short, we're going to call this Q because we don't need to look at V directly, and it takes us less time to write it. And of course, we know the area of whatever is lifting the wing or the tail or what have you. So we just have to remember what that is, but it doesn't change any. The only thing that changes is the angle of attack. And if we look at the lift of a wing, we can draw a little graph. And the lift of a wing is a straight line up until it stalls as the angle of attack increases. What that means is, and if we pick a single speed, so this number doesn't change, the area of the wing doesn't change, this doesn't change, only this changes, and this is our alpha, that the slope of this line, CL is what's left over after all these things are held the same, is the CL alpha that we're looking for. So it's just a number, just like any other slope, and it depends on the airfoil. But if we pick an angle of attack, we multiply it times the CL alpha, we get the CL, and then we multiply it times all these things, and we get the actual lift. So each of the wings of our airplane, try and draw this a little bit bigger because we have a lot to put in here, has some lift. There's our center of gravity. There's some weight. And there is a distance here we'll call front and rear. Okay. So we know these lifts and we know these distances. And the equation for a moment, which is what you get when you push on something at a distance and it goes around a circle, is just the length times the force. So the moments that we care about are, for example, times, sorry, that's an L, like that. Now, people are probably saying, well, but what if this isn't quite straight? Well, you're right, it's really a little bit different, but we're going to pretend these angles are small so that these distances are pretty close to right, just to keep the explanation simple for now. All right, so now we can redraw our graph. I'll draw it over here. We said that the lift is proportional to all these things, and when we write the equation for the moment, it's just L times all that stuff. So we have our Q for shorthand, we have our CL alpha times alpha, we have our S, and we have our L. The only thing that's changing in here is this. So we know that this is going to be a straight line, and depending on exactly where alpha is, it may or may not go through 0, and I'll explain that in a moment. But the slope of this line is going to be the slope of this times all these things. So if you've got a big S, for example, and a big L, this line is going to be steeper. If you've got a small s or a small l, this line is going to be less steep. So we draw this one, and we'll make this into the front one. So if this is a normal airplane, here it is from the top. And draw the wing quite the right place. This is the front wing, and this is the rear wing. You can see that this L is small, but this S is big, and this S is small, but this L is big. So these slopes are probably going to be pretty close together. It depends. Let's just say for now that this F times this L is smaller than this S times this L. What does that mean? That means that its slope is going to be a little bit less when we multiply all this out. So this is the front wing, and we'll draw the other one with a little bit, this one is bigger. The front one's the smaller one, so we'll draw this one with a little bit more slope. And this is angle of attack, just like before, except now this is the moment. Well, that's interesting. The lines cross. Why do they cross? Well, because lines tend to do that. If I actually drew this the way I'd written it, this is 0, because when m rear is equal to this, if alpha 0 and alpha 0, then this has got to be 0. So they cross. What does that mean? That means if the airplane is flying along here with alpha 0 and it gets bumped to alpha larger somehow, a gust hits it or something like that, m rear is going to become bigger. And that means it's going to push the nose more down than mf. So that means the sum of our forces is pushing the nose down, and the airplane's going to accelerate that way, and it's going to push the angle of attack back down. When it gets back to 0, then the forces go away because these are equal. If we go the other way, then this is the forward line. Down here at small angles of attack, or in this case negative angles of attack, now this is more nose up because it's the front one than this one, and it's going to tend to rotate the airplane the other way. So it's always going to return to this 0 position. So now we've found the equilibrium. The airplane wants to fly at a particular angle of attack, and if we change the angle of attack, it always wants to go back in that direction. There is a little problem though. This airplane wants to fly at a 0 angle of attack, and that's not very good. We'll talk about that in the next talk. Thanks for visiting the WhistlePig Classroom. We'll talk to you later. Take care. Bye-bye.